Okay, welcome to the PD reading seminar. It's my pleasure to introduce Youngho Kim, who is currently a PhD student at Indiana University under Professor Namle. This, and he will be a postdoc at Texas A&M with Professor Minh Tran. So today he's gonna talk about interior Harnack inequality and Hölder estimates for linearized Monge-Ampère equations in divergent form with drip. Please, Youngho.
Thank you, Professor Tran, for the introduction, and also thank you for the invitation. And I'd like to thank you all for coming to the talk. So, yeah, as introduced, today I'm going to talk about interior Harnack inequality and Hölder estimates for linearized Monge-Ampère equations in divergence form with drip. So, this talk is going to be based on a paper of the same title that has recently been published to Calculus of Variations and PDEs. So in the talk, I'm going to first introduce the equation, and then also introduce a little bit on the background of the results and the equation. After that, I'm going to state my results in the paper. And then I'm going to move on to explain some results for equations in divergent form that are related to the results of the paper. And then I'm going to conclude the talk by giving a sketch of proof for one of the results. Yeah, so the equation of interest today is this equation over here. That is a linearized Monge-Ampère equation with a drip term. So here, little b, capital B, and capital F are going to be bounded vector fields. And little f is going to be an ln function. Here, the matrix capital Phi is going to be the cofactor matrix of the convex function of the Hessian matrix of the convex function Phi. And then we're going to assume that the determinant of the Hessian of Phi is bounded between two positive constants, little lambda and capital lambda. So essentially, this is a linear elliptic equation where the ellipticity matrix, capital Phi, comes from the cofactor matrix of a convex function. So this equation is called the linearized Monge-Ampère equation because the second order term on the equation comes from linearizing the Monge-Ampère operator, as you can see from this equation over here. So linearized Monge-Ampère equations arises in several contexts in mathematics. So these are the list of some of the examples. So they appear in affine maximal surface equations in affine geometry. And the problem of finding Kähler metrics of constant scalar curvature, and then also semi-geostrophic equations in meteorology. And then they also appear in the solvability of singular array equations in higher dimensions in calculus of variations with a convexity constraint. So I'm going to introduce a little bit about some characteristics of the linearized Monge-Ampère equations before I move on. So the first point that I want to point out is that they are affine invariant. So if you consider the Monge-Ampère equations, which has the determinant of the Hessian matrix, because it is the determinant compared to uniformly elliptic equations like the Laplace equation, because it's the determinant, it's the product of the eigenvalues. So if you do an affine transformation where you kind of stretch in one direction and then shrink in the other direction, you still get the same equation. And then so a characteristic of the Monge-Ampère equation and the linearized Monge-Ampère equation is that they're affine invariant. And then because we are working under the assumption that the determinant of the Hessian is bounded between two constants, that means that only their product is bounded, and then the individual eigenvalues of the cofactor matrix, capital Phi, cannot be bounded by in terms of these constants, the dimension n and little lambda and capital lambda. So the linearized Monge-Ampère operator is an elliptic operator that can be both degenerate and also singular. The final characteristic that I want to mention is that the capital phi, the cofactor matrix, is divergence-free. And the linearized Monge-Ampère equation can be written in both divergence form and the non-divergence form because of this property. Okay, so the regularity theory of linearized Monge-Ampère equations was initiated in the pioneering work by Caffarelli and Gutierrez. So they proved that under the assumption that the determination is bounded between two positive constants, they proved an interior Harnack inequality for non-negative solutions to this linearized Monge-Ampère equation, where the constant only depends on n little lambda and capital lambda. Here, the S phi are the sections of the convex function phi that I'm going to explain later. So because the linearized Monge-Ampère equation can be written in both divergence and non-divergence form, the theorem of Caffarelli and Gutierrez can be viewed as an affine invariant analog of two classical theories for uniformly elliptic equations, specifically the theory of D. George, Nash, and Moser for equations in divergence form, and then the theory of Krylov and Safonov for equations in non-divergence form. The results of Caffarelli and Gutierrez have been followed by several other results by many authors. So to list the results for the equation where of this form, divergence of phi du is equal to little f. Gutierrez and Nguyen proved that if f is in LP with p bigger than n, and the determination is continuous, then the solution is in C1 alpha. And then they also proved that if f is in LQ with q bigger than n, and the determination is continuous, then U is in W2P for P smaller than Q. And then Le and Nguyen showed that if F is in LQ with Q bigger than half the dimension, then the solution is Hölder continuous. Okay, so now I'm going to move into linearized Monge-Ampère equations, where the right-hand side contains the divergence of a bounded vector field. So this is when things kind of get more interesting. So here, the term divergence F in our original equation, in the slide when I introduced the equation. So linearized Monge-Ampère equations with the divergence of a bounded vector field appear in semi-geostrophic equations in meteorology. Specifically, equations of this form, divergence of phi du is equal to divergence of F, appear in the study of semi-geostrophic equations. So for equations of this type, Rupert proved Hölder estimates when the determinant of the Hessian is close to a constant and the vector field is bounded. And then using fine properties of Green's functions, Le proved the same results with just the determination being bounded between any two positive constants in dimension 2. And then they also proved the Hölder estimates in dimensions greater than or equal to 3 under an integrability assumption on the Hessian matrix of the convex function phi. Here, assuming that the integrability is bigger than n times n minus 1/2, where n is the dimension. And then using D. George iteration, Wang proved that in dimensions greater than or equal to 3, Hölder estimates under this integral assumption. So here, if you assume that f is in L infinity, it's kind of assuming that the d square phi has integrability better than half the dimension. And then the difference here is that for this results of Le, it uses LP norm of U for P bigger than N, bigger than 1. But for the results of Wang, the L infinity norm of U is used. Okay. And the equation that I introduced to you earlier also has, in addition to the divergence of a bounded vector field, it has also drift terms. And linearized Monge-Ampère equations with the drift terms appear in the solvability of singular array equations in higher dimensions. So this is on a joint work of myself with Le, my advisor at IU, and then Wang and Zhu, these two other people currently at Peking University. So in this results, we have singular array equations of this form, where one of the key ideas of the proof is to transform this equation into this equation, which is a linearized Monge-Ampère equation with this drift term over here. So that is where linearized Monge-Ampère equations with drift terms appear. So they are connected to the solvability of singular array equations in higher dimensions. And then linearized Monge-Ampère equations that have drift terms but no divergence of a vector field have been studied by Le and Maldonado. But our equation involves all of these terms, including the divergence of a bounded vector field F, and then also these two drift terms. Okay, so before I state my results, I'm going to introduce two concepts to state the theorem. So the first concept is the section of a convex function. So because linearized Monge-Ampère equations are affine invariant, we need another object that is like that can play the role of balls for the theory of uniformly elliptic equations. And that is going to be precisely this object that are cross sections of a convex function. So if we have a C1 convex function, then we can define what is called a section of the function phi, centered at a point x naught with height h. So at this point, we have this tangent hyperplane, and then we look at the graph of the convex function, and we look at the points where the graph of the convex function is at most height h from this tangent hyperplane. So the set where the graph of the convex function, the height of this to the tangent hyperplane is smaller than h, is going to be this section s by x naught h. So these are going to be the affine invariant analog of balls. And yeah, if this convex function, for example, if the convex function is actually like just a quadratic function, then you can see that this is actually a ball in this case. And then, so these are going to be the objects that play the role of balls. And then we also say that this section S is normalized if it is between kind of balls of radius 1 and balls of radius n. So we call it normalized if it is kind of within these two. So we kind of have an estimate like so that it's kind of a nice shape and also not too small or not too big. The second concept that I'm going to introduce is the interior W21 plus epsilon estimate for Monge-Ampère equations. So this is the interior W21 plus epsilon estimate was proved by De Filippis, Bigalli, Sabin, and also by Schmidt. So if you have a solution to a Monge-Ampère equation where the right-hand side f is bounded between two positive constants, little lambda and capital lambda, then the W21 plus epsilon estimate tells us that the Hessian matrix is has integrability L1 plus epsilon in the interior. And what we have here is that this epsilon is a small constant that depends on the dimension n, and then these two bounds, little lambda and capital lambda. So this constant is small, but we know that if little lambda and capital lambda are very close, then they can be big enough under that assumption. And also we have from Sujia Wang's counterexample that if we cannot control the bounds little lambda and capital lambda, then this can be as small as possible. So remember that in the previous results that I mentioned, there were integral assumptions on that has to be imposed on the Hessian matrix of phi when we consider equations with divergence of a bounded vector field. So due to technical reasons, when I state the theorems, the integral condition on d squared phi will be imposed in such a way, saying that we have these little lambda and capital lambda, so that this d squared phi has a certain integrability. So that is how we use this interior W21 plus epsilon estimate. So this is going to be the first result that I'm going to introduce, which is a Harnack inequality for the equation that I introduced. So there are lots of assumptions here, but the thing to look out for here is this middle part. So we don't need any additional integrable assumptions in 2 dimensions, but in dimensions greater than or equal to 3, we use the W21 plus epsilon estimate to assume that d squared phi has integrally better than half the dimension. So we have this Harnack inequality under the assumption that this d squared phi has integrally better than n half. And based on this Harnack inequality, we can also obtain a Hölder estimate under the assumption that d squared phi has integrally better than n half. And here it uses the L-infinity norm of the solution U in the right-hand side for the Hölder norm. So in these two results, the constants depend on these values. So we have n, little lambda, capital lambda, and then r, and then the integrably epsilon star. And also it depends on the L-infinity norm of little b, capital B, and then also ln norm of the divergence of this vector field, capital B, inside the section. And it will also depend on the diameter and height of the section. So the next result is Hölder estimate with L2 norms. So here we are assuming a stronger integral assumption in dimensions greater than or equal to 3. So we assume that the integral is better than n times n minus 1 half instead of just being better than n half. Then we can show that we have Hölder estimate where the right-hand side now has L2 norm of the solution U instead of L-infinity norm of U. And the constants in this theorem depend on these, but it does not depend on the norm of the divergence of the vector field, capital B. So we have a stronger assumption on the integrability, but also prove a stronger result. So this is the L2 norm instead of the L-infinity norm. And then the constants do not depend on the norm of the divergence of the vector field B. Okay. So I'm going to go into the sketch of the proof later, but just to briefly mention the difference in the proof of this one and the results that I mentioned earlier. So the methods in this paper is different from the results of Le and Wang. So yeah, Le used fine properties of Green's functions and then also W21 plus epsilon estimate in 2 dimensions, and also Monge-Ampère subleft inequality that I'm going to introduce later when I get to the sketch of the proof. And then Wang used de Giorgi iteration and Monge-Ampère subleft inequality. Yeah, but we will use Moser iteration and the Monge-Ampère subleft inequality in our proof. Okay, so I'm going to now introduce some related results for equations in divergent form. So an extension of the theory for uniformly elliptic equations in divergent form kind of relaxes the assumption that the matrix capital A is has the lowest eigenvalue and the largest eigenvalue. So instead of assuming that these smallest and largest eigenvalues are bounded by two positive constants, they treat the smallest and largest eigenvalues as a function on each point. And then instead, you can assume that they satisfy certain interior condition. So mu is going to be in LP, and the inverse of the smallest eigenvalue, low inverse, will be in LQ. So Murphy and Stampaccia and Schrödinger showed L infinity and Hölder estimates under the assumption that these integral conditions P and Q satisfy 1 over P plus 1 over Q is smaller than 2 over N. And then Bella and Scheffler extended this result to equations of this form, where divergence of ADU is equal to 0 under a stronger assumption, under a weaker assumption that 1 over P plus 1 over Q is smaller than 2 over N minus 1. And this result is essentially sharp because there is a counterexample by Franci Serpioni and Sarah Cassano in dimensions greater than or equal to 4 when this 1 over P plus 1 over Q is bigger than 2 over N minus 1. So this is as far as we can go with these results. So now we have these results. Let's now look at the linearized Monge-Ampère equation case. So we are going to use the W21 plus epsilon estimate to kind of view this integrability of the smallest and largest eigenvalue of our cofactor matrix, capital Phi. So first, we know that the determinant Hessian is bounded between two positive constants. And we have the W21 plus epsilon estimate, which means that this d squared phi is in L1 plus epsilon. So from these two, we can show that this the smallest eigenvalue has the inverse of the smallest eigenvalue has the integrability of d squared phi, which is 1 plus epsilon from the W21 plus epsilon estimate. And because determinant of the Hessian is bounded above by capital lambda, and this is the product of the eigenvalues, this is greater than or equal to rho to the n-1 times mu. So we can also say that mu is in L of 1 plus epsilon over n-1. So we have P is equal to 1 plus epsilon, and Q is equal to 1 plus epsilon over n-1. And we can now calculate that 1 over P plus 1 over Q is equal to N over 1 plus epsilon.
Excuse me, sorry for interruption. Can you quickly remind me how you determine this epsilon star? Is this from your condition or it's something can be determined?
So this epsilon star is the epsilon from this W21 plus epsilon estimate. So yeah, through these slides, I'm going to use this epsilon star to denote the constant epsilon from this interior W21 plus epsilon estimate for Monge-Ampère equations.
I see. Thank you.
Yep.
So I mean, a follow-up question on this is exactly that you only have the result by Caffarelli to show you that epsilon star is going to be big enough if you have that one, right? Is there any other related result?
So not, yeah, like there's only this results to show that this is big enough. I don't know if any other results exist. So it's kind of, there is a conjecture that you can actually do a little bit better than this result by Caffarelli. But yeah, from my knowledge, I don't know anything other than this result. But we know that if they are close enough, then actually they can be big enough. So like is the statement of the theorems are kind of stated in a way so that we just have good enough lambda and lambda so that it has an integrability. Yeah.
Right. Cool. Thanks.
Yeah. Okay. So returning to this, this epsilon is the epsilon that depends on n lambda and lambda, and the one from this W21 plus epsilon estimate. So looking at the results of Bella and Schaffner, we want this 1 over p plus 1 over q to be smaller than 2 over n minus 1 in their condition. But here, this epsilon can be as small as possible when we cannot control the little lambda and capital lambda from Suzhou Wang's counterexample. So this is only guaranteed to hold for any little lambda and capital lambda when we are in 2 dimensions. And then in dimensions greater than or equal to 3, this condition is satisfied when 1 plus epsilon is bigger than n times n minus 1 half. And that is precisely the integral assumption that is imposed in theorem 3, which is the Hölder estimate with L2 norm, and the results of Le, which uses the LP norm of U instead of the L inferior norm of U. So this kind of exactly matches this condition. And so we can conclude that compared to the results of Bella and Schaffner, the theorem 3, the Hölder estimates with L infinity, L2 norm covers the case when we have all these extra terms, little f, capital B, little b, and capital F that are all non-zero. In the special case when the matrix A is the cofactor matrix of the Hessian of a convex function, d squared phi, which comes from linearizing the Monge-Ampère operator. Okay. So now I'm going to introduce the sketch of the proof of theorem 1, which is the Hölder estimate for, which is the Harnack inequality. So before I actually go into the sketch of the proof, I'm going to introduce one of the main tools, which is the Monge-Ampère Sobolev inequality. So this Monge-Ampère Sobolev inequality was proved by Tian and Wang in dimensions greater than or equal to 3, and by Le for dimensions 2. So we have this inequality over here, which says that the integral of phi dv dot dv bounds the LP norm of v, where this p can be any number between 2 and infinity in dimensions 2. And this p is exactly 2n over n minus 2 in dimensions greater than or equal to 3. So this is called a Monge-Ampère Sobolev inequality, because when we have the convex function as x squared over 2, then its Hessian matrix is the identity matrix, and the cofactor matrix is also the identity matrix. And what this tells is we can use the W12 norm to bound the LP norm of V, where the P is anything between 2 and infinity in 2 dimensions, and P is in 2n minus 2n over n minus 2. So in this case, this inequality becomes the usual Sobolev inequality, bounding the LP norm by W12 norm of V. So this is why it's called a Monge-Ampère Sobolev inequality. And yeah, this result tells us that when this phi is this special one coming from the Monge-Ampère linearization of the Monge-Ampère operator, then we can just treat this as an identity matrix. Even though it's not uniformly elliptic, we have this nice result for this. So this is going to be a crucial component in proving the results using Moser iteration, as we would have terms like this during the Moser iteration. Okay, so now I'm going to go into the sketch of the proofs of the theorems. So in the proof of the theorem, the first step is to use Moser iteration and Monge-Ampère Sobolev inequality to obtain inequality of this form. So if you have a self-solution, U, to the equation that's kind of smaller than or equal to 0 on the boundary of the section, then we can use Moser iteration to prove that the supremum is bounded by this expression involving the L2 norm of the solution, and then the norms of capital F and little f. And to get rid of this L2 norm, we use a trick in Gilbert and Schrödinger, where we define another function, W, of the form log of C over C minus U plus, where and then we obtain an L2 bound for this function. And then after that, we show that this W is also a sub-solution to this original equation. So combining this, we can bound the supremum of W using the L2 norm of the W, which is bounded from this step. So we have a bound for W, which actually implies a bound for U, for any U that is has less than or equal to 0 on the boundary of a section. So once we have established this, we apply that to U and negative U for solutions that vanish on the boundary of the section to obtain this estimate. And then, so we have this global infinite estimate. So we rescale this to kind of get results in any sections with zero boundary data. And then after that, we combine this with Harnack inequality for linearized Monge-Ampère equations that involve drift terms, but no divergence of the bounded vector field by leg. So we split the solution into the sum of two parts, where one part is the solution to a homogeneous equation but has the boundary data, and then the other part has zero boundary data but has all the terms from the right-hand side. So we bound one of those terms from the previous Harnack inequality, and then we bound the other term by this global L infinite estimate, and then combining them gives us the Harnack inequality. And then using the Harnack inequality, we can obtain the Hölder estimate in corollary 2. Yeah, so that is kind of the sketch of the proof. And then I don't have the sketch of proof for theorem 3, but I would also mention that the proof of theorem 3 kind of also uses the Moser iteration techniques and then the Monge-Ampère Sobolev inequality in the proofs. Okay.
Can I
So
can I ask
yeah,
a question before we
yeah,
so can you go to the Monge-Ampère Sobolev inequality?
yes,
So this is really beautiful. I just want to
yeah,
understand a little bit that can you explain sort of how do you go about to give the proof of that, and also like sort of do you use any specific structure of phi, because you say that phi is bounded from above and below, right? And you have
yeah,
the LP LQ regularity.
yeah.
Is there anything else you can use, or that is all for the property of phi?
So of course this phi comes from linear. So this capital phi
Right.
is the matrix that comes from the linearization of Monge-Ampère operator.
Sure.
So yeah, that is the structure required for this Monge-Ampère Sobolev inequality, and that is why it has the name like Monge-Ampère, and in terms with Sobolev.
Yeah,
And then
yeah, sorry, maybe let me phrase it in two
yeah,
parts so that it's clearer. Can you explain to us how do you go about to give the proof of this? I mean, that sort of.
um, Yes, so the proof of this uses the properties of green function for Monge linearized Monge-Ampère equations. So yeah, of course it has to yeah depend on the specific structure of that.
Yeah. And then the second question is that yeah, I understand phi is coming from the I mean the determinant of d square of var phi times d square var phi inverse, right?
Yeah.
Um, and then you have that is bounded from above and below by lambda x and mu x something, and then you use the bigness of epsilon star to have the LP LQ suitably. Um, is there any other sort of hidden structure that you can use, or that sort of that's all?
So this is kind of like my a little bit like speculation territory, but so in the related results, so of course like this has something other than the integrity to the matrix because like yeah it is kind of uh, a little bit does a little bit better than the results of Mertis-Tampesha and Schrödinger. So yeah, in their results, when they encounter four terms like this in the Moser iteration, so if we just assume integrability of this matrix, then we cannot have this full Sobolev inequality with this LP norm with P 2n over n minus 2. So you have this form, if you have replaced this phi by a, then it is bounded by the smallest eigenvalue times the square of dp, right? So you have to use Hölder estimates after that to kind of use the integrability of A inverse to kind of bound that. And then the resulting integrability of V you get from this will be lower than what you can get from the uh, Monge-Ampère Sobolev inequality if you just try to use the usual Sobolev inequality with the integrability of the eigenvalue. So yeah, I should say that there is some additional structure that makes this possible. And that comes from the special form of this V, but I should say I don't really understand what that structure is. Beyond that, there is something that makes this possible. Yeah.
Yeah.
Okay, so I can add some the information to what Youngho just mentioned. And so the proof of Stambaki Turing and all the work in the elliptic equation, usually that whether the right hand side is zero or non-zero, the proof carry over at the same time. However, what Youngho did is different. So here he need to use the Monge-Ampère overlap inequality. It means he need to use the Hölder and also the Harnack inequality for the right hand side exactly zero. When you do the Harnack for the right hand side exactly zero, no other term, you get the Monge-Ampère overlap inequality. So this need that hold Harnack inequality. But after you get the Monge-Ampère overlap inequality, you can treat the low order term by using this. So it's a iteration process from zero to non-zero. But the all other proof in the literature without Monge-Ampère structure, there's no structure, then you do the right hand side either zero or non-zero. You treat the same by the same argument.
Yeah. Great. Yeah. Okay. Yeah. So please continue, and then
Yeah. So this is going to be the end of the talk. Yeah. Thank you all for your attention. Yeah.
thank you, Youngho. Thanks a lot. We have time for questions, so please ask questions. Yeah, in the informal part, I will ask more about that because I want to learn more. But Yeah, while we are waiting, can I ask you, some of the, for me, I only know basic things about this, right? So the moment you get Harnack inequality, then you can do the normal iteration to get C alpha, because I imagine that your section, you can do a linear transformation to make it to be a standard section between B1 and Bn.
Yes, so in all the proofs, like so when using the Moser iteration, we assume the integrability of this convex function phi. So it's the bound will also kind of have this L1 plus epsilon norm of d square phi involved in the process. So we know that this phi is in L1 plus epsilon, but of course the L1 plus epsilon of the function phi will kind of depend on how big the domain is. So to kind of avoid having to care about the size of the section from the beginning, that is why we kind of first work in a normalized section so that this section is between B1 and Bn. And so because the function phi is convex, this section will also be a convex set. And it is a result by Fritz zone. So there's this thing called Jones lemma that you can, when you have a convex set in n dimensions, you can use affine transformation to kind of capture it between balls of radius 1 and balls of radius n, so that this convex set is like kind of like not too far off from an ellipsoid. So we kind of use that transformation to rescale the and the affine invariance property of linearized Monge-Ampère equations to rescale it so that the solution is kind of defined in a section that is normalized, so that we don't have to kind of care about the size of the section and the L1 plus epsilon norm of this square phi from the beginning. And then once we get estimates in this normalized section, after that, we use the rescaling argument to kind of get the results. And then, so at the rescaling, we would kind of use this transformation, and then that is when the height of the section comes into play. So yeah, that is how we would actually do this. So that is kind of the steps for the proof in the paper. Yeah.
Yeah. So I mean, basically, let's say that you can use the John lemma always to normalize a section to a standard section, right? And then you can do the normal iteration to go from Harnack to Hölder, right? I mean, with keeping track of all the sort of the width of the section and everything.
Yes. So going from Harnack to Hölder is kind of similar to like going from Harnack to Hölder for uniformly elliptic ones. So like you have this do this oscillation estimate where you have this oscillation defined as the supremum and minus infimum inside a section. And then you take a section of height half, and then you take this supremum minus the function and the function minus the infimum. And then like you use the Harnack inequality in this section of height half, and then you kind of add them together and then do the oscillation estimate to go from Harnack to Hölder.
Okay.
And then
okay. Are there other questions?
Yeah, hi. I have a question. Very nice talk, firstly. I want to ask, like, I noticed that your G term B is in W1N space. So I know there's a paper by Safanov in 2010. He proved like for Harnack encoded for non-differential form with G in Ln space. And over there, he construct the composition of the domain very nicely. So is there any connection between that paper?
Can you say that again?
Can you go back to the
results? Yeah, the G term over here.
Yeah.
is W1N space. So
Yeah.
did you use any like domain decomposition technique here? Or how do you deal with this W1N space, the condition for the drift term in this
So
space instead of just L infinity?
yes, so the theorems on this paper is about estimates and like so it's not like proving like regularly. So like it's just like so we assume these that these are nice enough, but like the constants just depend on the ln phi norm of little b capital B and then ln norm of divergence B for this one. So yeah. Yep. So yeah, so this if you look at this equation, then this second term gives something like u times divergence of B, right? So this divergence B kind of is like the lowest order term, like so it would be something like Cu in the theory of like uniformly elliptic equations. So yeah, we kind of need the ln norm of that in the estimate for the second well the second result, which is the Hölder estimate with ln phi norm. Yep, and then yep. So does that answer your question or
Yeah, maybe, but maybe I don't know much about Monge-Ampère equation, like so. Yeah, thanks.
Yeah, we can chat a bit more later. I mean, right after this, about
yeah,
the relation.
yeah.
Sure.
Can I ask one more question? So I understand that this has a background. This comes from the Monge-Ampère equation, but I'm wondering, do people also study parabolic type equation? So maybe time involving equation. Do people also consider that problem?
So yeah, I don't know much about like timed equation. Yeah, there might be some, but yeah, I don't know too much about those. So yeah,
Don't worry. Thank you.
yeah,
Okay, so let's thank Youngho again for a great talk, and then let's end now, and then we're gonna move to the informal discussion. So let me stop.